This is a video solution of problem 14 from section 7.7, where we're using Simpson's rule, and the number of subintervals being used in Simpson's rule goes from 4 to 8 to 16 to 32 in this problem, so that we can kind of see how the error changes as the number of subintervals doubles each time. And certainly as the size gets larger, you definitely want to use a computer of some kind to do this. But the first few are not too bad, and so I think it would be good to see an example of how Simpson's rule plays out. The one thing to keep in mind here is that when they're giving the n here for Simpson's rule, when we said that Simpson's rule was a weighted average of the midpoint rule and the trapezoid rule, there's a little bit of a disconnect between what the n means in those things. So it's worth to go through a couple of these by hand. So first of all, this function is the worst function I've seen in a while. What is going on with this? This seems really unnecessary, but okay. We have the function log of, I guess I'll have to move that down. Okay, we'll see how we can do keeping everything on the screen. Log of 16 plus 15 times cosine of x. All right. And they tell us the exact answer here is pi times log of whatever it is. So let's just keep track of that. If I evaluate that, let's see, I wrote these things down for my calculator, so I'm trying to just copy correctly. So I got about 7.47087 for this pi times log stuff that they say is the exact answer. And that's to at least 4 decimal places. So the real point of the question is to figure out how far down you have to go before you see this much error. But they want us to do it by just experimenting, by playing with the actual value as opposed to using the error bounds. So that is fine. We could play that game. All right, so the first thing we're trying to do is S4. So we know that S4 is a weighted average of the midpoint rule and the trapezoid rule. And we should use 1/3 the value of the midpoint rule and 2/3 the value of the trapezoid rule. But this is where the business about the ends is weird. What we refer to as S4 is really 1/3 of M2. I wrote that down backwards. Good Lord. It is Friday night and I'm talking to myself in my living room. 2/3 of the midpoint rule, 1/3 of the trapezoid rule. But the important thing here is that it's the midpoint rule with 2 subintervals and the trapezoid rule with 2 subintervals. If we draw the picture of this, I think you can see why that gets called S4. So I gave myself 2 pictures here so we can keep these 2 things straight. If I'm doing 2 midpoints, then I'm splitting my interval in half. This is pi over here. So the interval for this integral is 0 to pi. So I need to go halfway. Pi over 2 is right in that ballpark. So these are my strips. So remember, I'm first going to break my picture into strips. So there's 2 strips, and that'll be the same for the midpoint rule and for the trapezoid rule. I'm going to split the problem, or split the picture into 2 strips. For the midpoint rule, I'm now going to draw a rectangle across each of those 2 strips, and the height of the rectangle is going to come from the center of the strip across that, well, just the center of the strip. So in the first one, it'll be like that, and the second one will be like that. That dot is above pi over 4, and the second dot is above 3 pi over 4, halfway between the 2 values. And so in that picture, I can read off the height and the width of those 2 rectangles, and I can calculate M2. So M2 will be the width of the rectangle, pi over 2, times the height of the first rectangle, which is f of pi over 4. That's the y coordinate above pi over 4, plus pi over 2 times f of 3 pi over 4. So the sum of those two rectangles is the midpoint rectangle approximation M2. With trapezoids, I'm evaluating here, here, and here. I'm evaluating at the ends of the strips. And what I'm evaluating is not just the single height, but I'm going to try to draw straight lines between the dots. And then I can calculate the trapezoid as the width times the average height. So the average height is going to be f of 0 plus f pi over 2 over 2. So that's the first trapezoid. And the second trapezoid, I would add to that, plus second trapezoid is width pi over 2, and the average height is f of pi over 2 plus f of pi all over 2. So width times average height there. So just those two trapezoids together will be my T2 approximation. So I know that's a bit of a mess to look at, but that's how I would get the M2 and the T2 approximations. And then the S4 approximation will be 2/3 of one of those plus 1/3 of the other. That'll be S4. And I worked it out for this particular problem. That is 7.5515 to 4. Hang on. So that would be the answer to, well, so the answer to 4 decimal places is 7.5515. That's the value of S4. And so that would go in this box over here. And so that's just one of the answers. Now, the reason this is called S4 is because if I had drawn all of those dots on the same graph, rather than drawing on two separate graphs, it would have looked like dots that were drawn by cutting the picture into 4 pieces instead of 2 pieces, because the dots are different, right? The dots here are above pi over 4 and 3 pi over 4, and here they're above 0, pi over 2, and pi. So if I drew all those dots in one picture, it would look the same as if I broke the interval up into 4 subintervals and then evaluated the graph across the top. So that's why, and you can think of it that way. There's a totally legitimate interpretation of Simpson's rule, where you're thinking about a calculation on 4 subintervals instead of 2 subintervals. So that's why it's called S4, but it is equivalent to 2/3 of M2 plus 1/3 of T2. So this is how we can always do our calculation. Okay, so let me try one other one. Maybe I'll just do one and just tell you what the answer is to the other one, because this is very cluttered. So here I have 2 pictures. I'm going to get rid of one of them. And let's suppose that I am trying to do, I want to do the S8 calculation. And so I know that is 1/3 of the T4 calculation plus 2/3 of M4. So I need T4 and M4. So let's let me do M. I think M is a little weirder. So on this picture, we'll do the work for getting M4, and I'll just tell you what I get for an answer, so you can check. All right. So the M4 calculation. First, I'm going to break my region up into 4 pieces. That's not very good. That's not much better. So that's pi. That's pi over 2. Halfway between will be like that. 3 pi over 4. Halfway between will be here. That's dreadful, but okay, pi over 4. So just pretend those are equally spaced. So we break it into 4 pieces. For the midpoint calculation, I need halfway in between each of these. And so halfway here is pi over 8. Halfway here, halfway between pi over 4 and pi over 2 is 3 pi over 8. Halfway here is 5 pi over 8. And halfway here is 7 pi over 8. So those are the x-coordinates of the 4 dots that I drew. So the midpoint rectangles are going to have a width of pi over 4. So the width will be pi over 4, and that'll be the width of every one of these rectangles. Again, once you suspend disbelief about my my drawing, they're supposed to be equally wide, and all the widths are pi over 4. And so that quantity can be factored out of the sum. There's no reason to do pi over 4 times the first y-coordinate plus pi over 4 times the second y-coordinate, and so on. I could just do pi over 4 times the sum of these, and so I'll have f of pi over 8 plus f of 3 pi over 8 plus f of 5 pi over 8 plus f of 7 pi over 8. And if I do that, that's approximately, where did I write that down? Just so you can check, that's 7.512728 and more stuff. So again, since I'm going to have to get 4 good decimal places at the end, I want that calculation to be good to a couple of extra decimal places, just so I don't have any rounding problems when I put it all together. So that's what the M4 calculation would look like if now in a different colored pen, let's do a red pen. If I pretend like I was doing the trapezoid approximation, I would put my dots at the edges of these strips, and I would draw straight lines in between the dots. And now I'm going to do a trapezoid calculation for each one of those. The width of each trapezoid is pi over 4, just like it was for the midpoints. But now I have to do the average height of the first trapezoid, the average height of the second trapezoid, and so on, and add those up. And if I do that, I get T4 is 7.42666. It's the approximation of the double, 0, 1. So I have T4 and M4. I can put those together to be S8. And so S8 to 4 decimal places will be, oops, not O point anything. 7.4 840 looks like. So that'll be my Simpson rule approximation. Again, that's just doing the weighted average, 2/3 of the midpoint answer and 1/3 of the trapezoid answer. Anyway, and you can see from this picture, when I draw them on the same axis or the same graph, you can see, if you think about these dotted lines coming down from those midpoint dots, you can see why you would consider that S8. There really does look like 1, 2, 3, 4, 5, 6, 7, 8 subintervals across the bottom. But it's because the 4 subintervals for midpoint and the 4 subintervals for trapezoid all use different y coordinates, and so you ends up looking the same. All right, I think that's good. I would not do S16 or S32 by hand, I would Google, look for a Simpson drill calculator to do those values.